My name is Robin. As was mentioned, I'm a PhD student in the University of Illinois at Urbana Champaign. And today I want to talk about my micromagnetic simulation project on generating multiple magnetic droplets from exotic spin orbit torques. And before I start, I want to thank my funding source, the NSF MERSEC. And I also want to briefly mention that we recently published a paper on this project. So if you're interested in reading more about this, I encourage you to take a look at it, and there's more information than what I can talk about here. So to start, I want to briefly introduce magnetic oscillators, which have nonlinear dynamics as a function of electric current and magnetic field, and they can couple to each other, which makes them really interesting for new neuromorphic computing applications. And there's two types of mechanisms, or two main types of mechanisms to excite these oscillators. One is the spin transfer torque and the other the spin orbit torque. So in the spin transfer torque geometry, the current is sent perpendicular to this magnet stack, and it's first sent through a fixed magnetic layer where the electrons get spin polarized in the direction of the magnetization of the fixed layer, and then they go through a spacer layer and then into a free magnetic layer where the spins exert a torque on the magnetic moments of that layer and drive the local damping to zero, and that causes the magnetization to oscillate. And then in the spin orbit torque geometry, a current is sent in the plane of a heavy metal such as platinum, and due to the spin Hall effect, there's spin-dependent scattering of electrons, and you also get a spin accumulation at the interface between the heavy metal and the free magnetic layer. And similar to the spin transfer torque geometry, the spins exert a torque on the free layer, drive the local damping to zero, and cause the magnetization to oscillate. And it's been shown with both geometries that multiple coupled oscillators can provide new functionalities for information technology. And then a different kind of oscillator that can be generated from spin torques is a magnetic droplet. And this is a dynamical soliton that occurs in a ferromagnet with a uniaxial out-of-plane anisotropy. And it's characterized by a circular core whose magnetization is opposite to that of the bulk of the material. And the moments between the core and the bulk recess homogeneously through a full 360-degree rotation and at precession angles of up to 90 degrees with respect to the bulk of the material. And they were first experimentally realized using orthogonal spin valves with a nanocontact spin transfer torque geometry, where spins were given a out-of-plane, so Z component, and were then injected into the free layer and were able to generate this droplet. So it's important that the spins have a Z component to them in order to efficiently switch the magnetization of this PMA material. But with this geometry, you can only nucleate one droplet at a time, and the droplet is locally confined to that nanocontact region because that's the only region where the spins are injected into the free layer. So what we want to investigate is if we can use spin orbit torques instead of spin transfer torques to generate multiple magnetic droplets instead of just one. So why is spin orbit torque more interesting? So in the spin transfer torque geometry, as I mentioned, there's only a local injection of torque at the site where the fixed layer and the free layer meet. And the fixed layer usually has to be, or this kind of cylinder shape usually has to have small diameters in order to get high current densities. So spins are only injected into a small area of the free layer. And then in the spin orbit torque geometry, on the other hand, you get non-local injection of torque. So spin accumulations are generated over the whole surface or the whole interface between the spin orbit torque layer and the free layer. And you get high current densities even for large free layer areas, because you don't have to send the current perpendicular, but you send it in the plane of the material. So you can get high current densities by decreasing the thickness of the spin orbit torque layer without having to reduce the size of the free layer. So spin orbit torques can be used to efficiently inject large torques over large areas than with the spin transfer torque geometry. But the problem with spin orbit torques is that conventionally, when you send a charge current through your spin torque generating layer in the x direction, you generate a Z spin current, and these spins have a polarization that only points in the y direction. And as I said earlier, we need spins that also have a z component. But in order to do this, we can use materials that have a broken symmetry through either their crystal structure or their magnetic structure, such as manganese 3 gallium nitride. And here a charge current along the x direction generates a spin current along the z direction. But now the spins can not only have a y component, but they can also have an x component, or more importantly, for our case, a z component. So with this unconventional z component, we can inject torques into out-of-plane torques into a free layer and should hopefully be able to nucleate or generate magnetic droplets. So in order to investigate this, we use micromagnetic simulations using MUMAX, and we have a ferromagnetic layer where we use typical material parameters for a cobalt-nickel multilayer, which includes a uniaxial anisotropy along the z direction, which makes it have a perpendicular magnetic anisotropy, which is what's necessary to generate these droplets. And then we don't specifically simulate this, but this spin-orbital layer, but we can imagine that it's below the ferromagnet, and here a charge current in the x direction generates a spin current in the z direction with a spin polarization that lies in the yz plane as dictated by a combination of the conventional and unconventional spin torques. And as usual, the dynamics in our simulation are governed by the Landau-Lifshitz-Gilbert equation, where the spin-orbit torques enter through the Slanchevsky spin-transfer torque term, and this allows us to set any arbitrary out-of-plane spin polarization angle phi, so we can do our simulations with different out-of-plane angles. And we also apply an external magnetic field only along the z direction. So let's look at some of our results. So here we see a top-down view of the ferromagnetic layer, and the gray regions here represent moments pointing out of the screen, the black region moments pointing into the screen, and then the color represents in-plane moment directions, as you can see on this color wheel on the right. And we use an out-of-plane angle of 50 degrees and then apply a DC charge current through that spin-orbit torque layer, basically. And we apply an external magnetic field. And we can see that 5 nanoseconds after we started to apply the current, we see a droplet that has formed in the center of the ferromagnetic layer. And then after more time, we can see that 2 more droplets nucleated on either side of the first one, and that the first one has grown in size. So from this, we can already see that because we're injecting currents or spin torques over the whole ferromagnetic layer region, we're able to generate multiple magnetic droplets instead of just one, as in the nanocontact geometry. And then with further time, we nucleate a third set of droplets, again on sides here, but we can already see that the first droplet has kind of shifted in shape, and the oscillation in this region here is not homogeneous anymore. You can see different colors, as opposed to here is just one single color. And then with more time, the magnetization landscape becomes chaotic because droplets combine and nucleate and kind of move toward the edges and expand, and the magnetization landscape just becomes chaotic. So we can already see that we can generate multiple droplets, but that the nucleation current is too high to sustain the stable oscillation of them. So what we can do is use a short high current pulse in order to nucleate the droplet, and then we reduce the current to keep more droplets from forming and to keep the droplet from expanding outside of the boundaries of the ferromagnet. And what we can do here is we can use longer current pulses. So with a longer pulse, we can nucleate 3 droplets and then reduce the current again in order to keep all 3 droplets stable. So yeah, we can stabilize the droplets by reducing the current, and because we're injecting torque over the large area, we can control the number of droplets we have in our system with different current pulse lengths. And we can also switch the number of droplets. So we can use a high current pulse to generate 3, then reduce the current to keep them stable, and then use a lower current pulse to annihilate the 2 outside droplets here. So we're left with only 1. And then again, the high current pulse can be used to nucleate more droplets and so on. So we can use specific current hysteresis to vary the number of droplets in our system. And then finally, we looked at the nucleation current as a function of the out-of-plane spin accumulation angle and as a function of the applied magnetic field. And then we can see that as we decrease the angle, we need a higher charge current in order to nucleate the droplets. And this is because with small angles, we have a smaller Z component of the spin polarization, which is the one that's efficient at generating these droplets and switching the PMA magnetization. And then with higher magnetic fields, we also need a higher current, so a higher spin injection, because at higher fields, the moments are more rigidly coupled to, or more rigidly in the direction of the magnetic field. So we need a larger torque and therefore a larger current in order to tilt them away from that direction. So in summary, I've shown that we can nucleate multiple droplets with an unconventional spin orbit torque that has a Z component of the spin polarization. We can stabilize the droplets by reducing the current after a high and short nucleation current pulse. And we can vary the number of droplets in our system because we inject torques over the whole ferromagnetic layer region instead of just a small region at the center. So yeah, I'll be happy to take any questions, and you can email me your questions if you want. And if you want more information, again, you can check out our paper on this. Thank you.
Thank you, Robin, for a very nice talk. We have a question in the chat. What defines the maximum number of droplets generated before chaotic behavior occurs?
So I think one thing is the width of the region, because the droplets eventually expand towards the width of the region. So if the region were wider, you would be able to grow the first droplet more, which might enable you to generate more and more droplets. And then the other thing is how far above the necessary nucleation current you are. So if you apply a higher current than necessary, you will also generate more droplets more quickly, and then they will expand more quickly and things become chaotic more quickly. Yeah.
Great. Thank you. I don't know, Petro, if that answers your question. Yeah, thank you. I have a question myself. It draws my attention, the similitude of one of the droplets to an hexagonal shape. Is there any tendency to form any other shapes other than spherical or circular shapes?
Yeah, so there's a few other papers that have seen, so what I've mostly seen is these, maybe you can see it here with the turquoise, it's kind of hexagonal, but there also exists like triangular shapes, and that I think, and there's also elliptical shapes, and that, from what I can tell, it depends on, in my simulations at least, depends on the magnetic field that I apply. So with smaller magnetic fields, they tend to be more elliptical when they grow, and then with larger fields they tend to be more hexagonal, and then in between it's like a triangular structure. So I think these correspond to different frequency modes in the droplet.
That's very interesting. We have another question in the chat. Have you or your collaborators combined the simulations with experiment or intent to?
Yeah, so we haven't.
Yeah, go ahead.
Okay, yeah, so we haven't, so we've definitely thought about it, but we haven't done the actual experiments. So we're also working on, right now we're working on a material that can also produce out-of-plane spin polarizations. And then once we have that, we can try to see if we can nucleate these droplets also experimentally. So we have a plan to do it, yes.
Yeah, the question continued with the shortness of the pulses seems tricky to realize experimentally. So
yes, that's definitely the other thing. We were thinking about how to get such short current pulses. But yeah, they're on the order of 10 nanoseconds, something like that, which is, I think, not technically impossible. It just requires very good equipment. So I think it's doable if you have the right equipment to do so.
Sure. Yeah. Sorry, I skipped one question in the chat. Matt asked, can you manipulate the current or the field to make the solitons approach each other to see if or how they would interact?
Yes, so I believe that you can apply external magnetic fields that are not perfectly in the Z direction, but have some either X or Y component to make the droplets move. People have done this in other papers with the nanocontact geometry. I've tried it with my simulations here, but I couldn't really get it to work very well, because as soon as I applied a field in a different direction, the magnetization landscape became a little more complicated, and droplets weren't forming very well. So it's definitely possible to move them with another field, but yeah, I haven't successfully done so in my simulations.
Right. Thank you again, Robin. It was a great talk.